Hello everyone, welcome to Basics e-learning.
In lesson number 3 video, I am going to explain different properties of Fourier series. In my previous lectures, I have explained basics of signals and systems and numericals based on that, Z transforms and problems based on Z transforms completely. All the questions are collected from previous question papers and also few lectures of network analysis are also there in the channel. I am providing the link of each playlist in the description box. Please check it out. Also, students who need online classes can contact us through the mail ID mentioned in the description box. In the previous lecture, I have explained what is a Fourier series, on what signals we can apply the Fourier series, also the conditions to converge the Fourier series called Dirichlet conditions. Before starting this video, first go through the two videos, then you can understand the properties of Fourier series very easily. The different properties of Fourier series that I am going to discuss today are linearity, time shift, frequency shift, scaling, time differentiation, convolution, modulation property, and also Parseval's theorem. As we have 8 properties and each property derivation is little lengthy, the explanation may take time, so that's why I'm releasing this properties of Fourier series video in 2 parts. Please note it. Let us see the first property, linearity. So consider two signals x of t and y of t. So if you apply Fourier series on x of t, you will get x of k. Similarly, if you apply Fourier series on y of t, you will get y of k. Then let us take a combination of the signals x of t and y of t. Let us call it as z of t. So z of t is equal to ax of t plus by of t. Now if you apply a Fourier series on this z of t, you get z of k. Then z of k is defined as ax of k plus by of k. Now let us see the proof for this property. We know Fourier series can be applied only on the periodic signals. So x of t and y of t both should be periodic signals with a time period t is equal to 2 pi by omega naught. Say the time period for x of t and y of t is equal to 2 pi by omega naught. Now, so you take this z of t and let us apply the Fourier series on z of t, right? So z of k will be 1 by t, as I think you remember the definition from the previous video. 1 by t integral over t z of t e power minus j k omega naught t dt, right? This is the definition for Fourier series. Now we know z of t is equal to ax of t plus by of t. So replace z of t with ax of t plus by of t. So I am doing that 1 by t integral t. In place of z of t I am writing ax of t plus by of t multiplied by, as usual, the remaining thing I am writing minus j k omega naught t dt, right? Now let us split the integration over this summation. Now this will become 1 by t. You can write it outside, it will not do anything with the integration, right? Integral t x of t e power minus j k omega naught t dt plus b, you can write it outside, 1 by t integral y of t e power minus j k omega naught t dt, right? As you remember from the definition here, x of t, x of k is nothing but the Fourier series of x of t. So that by definition you can write integral x of t e power minus j k omega naught d dt is nothing but the Fourier series of x of t. So this part is nothing but Fourier series of y of t. So Fourier series of x of t is x of k and Fourier series of y of t is y of k, right? Hence it is proved. So only thing that you have to remember is the definition of your Fourier series. Once you remember the definition of Fourier series, simply you can replace this z of t with the ax of t plus by of t, then you can simplify this very easily. So this is the property of linearity. Coming to the second property, time shift property. If x of k is the Fourier series of x of t, then a shift in the time domain signal, that is in x of t, if suppose it is shifted by t naught, that is the signal becomes x of t minus t naught, then what happens to the Fourier series of such signal? Then its Fourier series of the signal x of k is multiplied by e power minus jk omega naught t naught. Let us see the proof. This is again very simple. Let us call this x of t minus t naught be z of t, right? So for this z of t, I am trying to find out the Fourier series. Let us call the Fourier series be z of k. Then it will be 1 by t integral 0 to t, integral over t z of t e power minus jk omega naught t dt, right? So replace this z of t with x of t minus t naught, as you have assumed z of t as x of t minus t naught, right? So I am writing, then again minus jk omega naught t dt. Now you can simplify this integration. So in the previous case we have a summation, so simply we have divided the integration over the summation, but here we have only one term x of t minus t naught. So let us call this t minus t naught by lambda, right? Now you find out this, what is this dt value. So apply both the sides, you go for differentiation. So dt will be d lambda, because t naught is some constant. Shift no, minus 2, 3, 4, any number, that will be constant, right? So now dt will be d lambda. Then what happens to t? From this, t minus t naught is nothing but t is equal to lambda plus t naught. Now we are completely changing the order of differentiation from t to lambda. Let us do that. Now we can simplify this. 1 by t integral t x of lambda. So I am just splitting this one, e power minus jk omega naught lambda and e power minus jk omega naught t naught d lambda, right? So as this integration is over lambda, the lambda terms I am keeping it inside, and the term that is related to t naught is now constant, that you can write it outside. So that I am writing e power minus jk omega naught t naught 1 by t integral over t x of lambda e power minus jk omega naught lambda d lambda, right? So if you observe, this is nothing but the Fourier series definition, right? As it is in terms of x, this I can write it as x of k. So this is x of z of k here is nothing but e power minus jk omega naught t naught multiplied by x of k. So this is nothing but your time shift property. See here. This is the definition of time shift property, and I have proved. So a shift in the time domain makes the Fourier series signal, that is x of k, multiplied by e power minus jk omega naught t naught. So the time shift in time domain causes this frequency shift in the frequency domain. Let us see the third property, frequency shift. So a shift in the frequency of a time domain signal then causes a shift in the signal of x of k, that is a shift in the Fourier series signal. See, x of t, let us take one signal x of t, and the Fourier series of the signal is x of k. So if you are applying a frequency shift on your x of t, that is e power jk naught omega naught t, then the signal, the full signal itself is shifted on the x-axis by the same amount. Let us see the proof here. Again, the same way, apply Fourier series on z of t, that is z of k is equal to 1 by t. I am just writing the definition, right? Z of t e power minus jk omega naught t dt. Now replace z of t with the signal that you have assumed. That is 1 by t integral over t e power j k naught omega naught t x of t multiplied by e power minus j k omega naught t dt. Right? Now here you have both are of having same base and the powers can be added here. So that I am simplifying this part as 1 by t x of t, okay, integral over t x of t e power j k naught omega naught t minus j k omega naught t dt, right? So you have j naught omega naught t common, so that you can take it out, integral x of t e power j omega naught t you can take out, that the remaining will be, so minus also you can take out because Fourier series definition you have e power minus jk, right? So minus j omega naught t, that will be k minus k naught dt. So if you observe the definition of Fourier series, z of k is equal to 1 by t integral over t z of t e power minus jk omega naught t dt. Now what you are getting? Minus jk omega naught k minus k naught into t. So instead of k, here I have k minus k naught. If I have k, I am writing the Fourier series as z of k. But here I have k minus k naught. So this you can write it as z of k minus k naught. As I have in the power I have, as I have k minus k naught, I am taking it as z of k minus k naught. This is also very simple definition, right? So only from the definition I am going for the proof of this frequency shift on Fourier series. Very simple. Next is scaling. If x of t has a Fourier series of x of k, then x of at, the scaled version of the given x of t, also having the Fourier series as x of k only. This is how. Let us go through the proof to know how it is happening. So, let us take the signal x of t, right? So, let us take x of t is a periodic signal and let us call this z of t as x of a t, right? So, again x of a t also has to be periodic signal, then only we can apply Fourier series, right? So let us say the fundamental period be t, right? So then the fundamental period of x of at will be what? For x of t, I am taking the fundamental period of t. Then for x of at, the fundamental period will be t by a, isn't it? In place of t, I have t, but at, it will be t by a. So to understand the periodicity property, go through the basics of signals and systems where I have explained the periodicity property very clearly. The link I have mentioned in the description box, please go through. Now, x of t has the fundamental frequency of omega naught. Then this has fundamental frequency will be a times omega naught, right? So the time period and the fundamental frequency of the time scaled signal are t by a and a by omega naught for z of t. Now let us write down the definition, right? So that is, x of k means I am writing the Fourier series of x of t. X of k is equal to 1 by t integral over t x of t e power minus j k omega naught d dt, right? Now let us write for z of k now is equal to 1 by the fundamental time period of x of k I wrote here. Now I have to write the fundamental time period of z of t. The fundamental time period of z of t is t by a. T by a integral over t z of t. So z of t is nothing but x of a t. Okay, that I'll write it in the next step. E power minus j k omega naught. Omega naught is nothing but a omega naught for z of t multiplied by t, then you have dt, right? Understood? Here This is the definition of your x of t, Fourier series of x of t. That means x of k. 1 by t integral over t d x of t e power minus j k omega naught t dt. Means here t and omega naught are the fundamental time period and fundamental frequency of x of t. As I am writing the Fourier series definition for my z of t, here I have replaced the fundamental time period and fundamental frequency of z of t as t with t by a and omega naught with a omega naught, right? Understood? Now this you can more simplify further as this is nothing but a by t. Even here also over the time period t, the fundamental time period is nothing but t by a, right? So z of t is nothing but x of a t, right? This is e power minus j k a omega naught t dt, right? Now let us call this a t is equal to lambda. Then you differentiate, right? So if you differentiate it both the sides, right, a into dt is equal to d lambda. So dt can be replaced as 1 by a d lambda. Understood? I have just differentiated on both the sides. Now I am replacing the order of differentiation from dt to d lambda. Let us do that. So z of k can be written as here a by t integral over t by a, right? So x of a t, that a t is nothing but lambda here. So that is x of lambda e power minus j k omega naught lambda, right? A t I have here again, right? So wherever a is there, I am just replacing, t is there, I am just replacing with lambda, right? So that is lambda into dt can be replaced as 1 by a d lambda, right? Understood? What I did is, again I am explaining a t and taking it as a t as lambda. Now differentiate on both the sides so that I can replace dt with lambda, right? So a into dt is equal to d lambda. So dt can be replaced as 1 by a d lambda. And in the power also I have that at term that I am replacing with lambda. Here x of at I am writing it as x of lambda. So now if you closely observe this one, see a by t integral over t by a x of lambda e power minus j omega naught lambda 1 by a d lambda. So here this lambda a also will get cancelled. No, a is constant only. Now this is nothing but 1 by t integral over t by a x of lambda e power minus j k omega naught lambda d lambda. Again this is the basic definition of Fourier series, right? That is nothing but x of k in terms of x only, no? So x of k. So z of k is nothing but x of k only. That means the Fourier series coefficients of here x of t and z of t both are same, right? X of t and z of t. Z of t is what? The scaled version of x of t, means x of at. So the Fourier series coefficients of x of t and x of at both are identical, but the harmonic spacing is different. There you have only fundamental time frequency is a omega naught, but here you have a omega naught. Other than that, the coefficients are same, though you time scale the signal in Fourier series.
For more videos, please do like, share, subscribe to our channel. Let us know your suggestions and queries in the comment box. Thank you.